I hope you had some time to work on this example in the meantime. Yeah. Any questions like what we're trying to do over here? Right? By putting everything in a single table, we get to see a clearer picture about the relationship between Q1 and Q1 plus and what we need at JK, without having to worry about that special construction, the order of a K-map. All right. So this is actually the same example as before. So you can refer back to the previous slides to see what you should get at each row. Right? But it's kind of different. It's actually different. Because in the implementation part, we can put down some don't cares. And these don't cares allow us to simplify or minimize the expression. Right? Whereas from the analysis perspective, everything is already fully specified. You just run a perfect evaluation with all the specified values. Right. So let's do it together. So for me to go from 0 to 0, let's say I'll do Q1 first. So I look at the excitation table, look at the relationship between Q1 and Q1 plus. 0 to 0 can be done by 0x. Second row, 0 to 0, 0x, 0x, 0 to 1, 1x, 1 to 1, x0, 1 to 0, x1, 1 to 1, x0, 1 to 0, x1. Right, these are the values I need to put at the JK inputs to enable that transition to happen. And then I will move on to Q0. Right, and look at this column for Q0 and Q0 plus. Again, I'll do some recovery. So 0 to 0 requires 0x, 0 to 1 requires 1x, 1 to 1, 1 to 1, both are x0, 0, 0, 0x, 0, 1, 1x, 1, 1, x0, finally 1, 0, x1. We actually did this yesterday when in K-maps, but now we're doing this in this table. Right? And after that, you're trying to implement J1, K1, J0, K0 as a combinational function. And this, you already have the truth table. You know how to do that. Right? Put that into a K-map, find the minimum expression, and then write out that function in whatever way you like. And that's the implementation. That is a component that we can put before the two flip-flops to enable them to work according to this state table. All right. Let's do it one more time in K-map. I prefer this method because with that table, you shouldn't have to draw a K-map so that you can do logic minimization. But if you directly do this process in a K-map, then this is your singular place for both representation and also optimization. Right? But essentially, I'm following the same principle. In a K-map, well, I'm trying to build a combinational function with 3 inputs, Q1, Q0, the state, and the primary input x, with an output of Q1 plus and another output of Q0 plus. These are 2 separate outputs, so they have to be implemented separately. From the first table, I want to observe the relationship between Q1 and Q1 plus. Right? So essentially between this column and the values inside the table. Like the values inside the table are my Q1 plus values, and that column represents Q1. Right. So here, Q1 is going from 0 to 0, so I put down 0x. Right. In fact, all of these are 0x because they sort of have the same previous Q1 value and the new Q1 plus value. I can do it group by group. Instead of 1 to 1, I just find all of these conditions that share the same current state and next state behavior, and then do the translation once. And then for here, Q1 is a 0. Q1 plus is a 1. 0 to 1 can be done by 1x. Right. Coming to the bottom half, Q1 is 1. And 1 to 1 can be done by x0. 1 to 0 can be done by x1. Right. In fact, with JK implementation, you always have half of the table being don't cares. And that allows for logic minimization. right? You can group this one with don't care to get a larger implicant so that it can be implemented more cheaply. This is a prime implicant, and then this is a prime implicant. So you can now say that J1 equals X Q0, K1 equals X. So coming to the second table for Q0, well, I'm trying to compare the relationship between Q0, which is that column in the header, and Q0 plus. The first entry on the top left, 0 to 0 transition, can be done by 0x. And also at the bottom, that's a 0x. Top and bottom row share the same condition on Q0. And 0 to 1 can be done by 1x, so 1, 1, xx. In the middle, Q0 is 1, and 1 to 1 is x, 0. 1 to 0 is x, x1. Again, we find the minimum expression, which is J0 equals x, and then K0 equals x Q1. And with that, we directly translate them into some gates. J1, K1, they become a single AND gate. K1, J0, you connect them directly to the primary inputs. And that's your circuit. That's your implementation from the behavior described in the FSM table. And the output function, you simply put that in a truth table or K-map and then minimize it. Right? It doesn't have anything to do really with the internal behavior of the flip-flop. Yeah, any questions? Yes? The previous one? Yes. So I think I should highlight a few examples. So let's say, look at the second K-map. This K-map sort of describes the relationship between Q0 and Q0 plus. Q0 is one of your input. Q0 plus is the output. Right? So to make that transition happen within the flip-flop, we need to compare them and to see what we need to put at the J input and K input. So for example, so let's say we look at this one. That tells me if my current state is 1 on Q0, and based on that state and the input condition, the next state should be a 1. So I really want Q0 to move from 1 to 1. Q0 needs to move from 1 to 1. Well, what do I need? I need to put x0 at the JK inputs. And therefore, I put x over here and 0 for k. Right, highlighted one example, right, second row, second column. That's a 1-to-1 transition on Q0. So for the Q0 flip-flop inputs, I need to put x and 0. I need to send these values after that combination logic. Right, from that combination logic, they need to produce x, or don't care over here, and the 0 over there to activate the transition. What about this previous table? Are you comfortable with this one? Well, let me find the same example from the previous table. So 0, 1, input is 1. 0, 1, input is 1. That's this example. Current state 0, 1, input is a 1 based on the state table. Next state will be 1, 1, which means Q1 moved from 0 to 1. Q0 moves from 1 to 1. For Q0 to move from 1 to 1, based on the excitation table, requires x0 on the JK inputs. I think this table gives a better picture about the interaction between the combinational function and the state transition behavior within the flip-flop, whereas the K-map is a better implementation tool. But you can also do the same analysis, like whatever you can do with a truth table, you can do it in a K-map. Although with the actual dimension, it might not look that straightforward, like the way we look for the Q column and the Q0 plus values. But it's really, we just check for each flip-flop individually, relationship between Q1, Q1 plus, Q0 and Q0 plus. And based on the excitation table, convert that single transition into two separate values. Any more questions? All right, so we just complete our implementation task. So to sum it up, you can do FSM analysis by simulating a circuit or using Boolean algebra. You can implement FSM by drawing that large state table or directly fill out the K-maps and doing logic minimization based on the excitation table of the flip-flop. And that's really this part of our learning objectives, the conversion between state graph and the implementation. There's still a missing question, like how do we convert a casual description into some FSM graph or table? Right? Like if I ask you to design a thing like a vending machine, how do you model it in the state graph using nodes and transitions and input-output values? So that's the next part of our conversation for today, design state graphs from behavioral descriptions. Do you know shape-up? Have you heard about it? No? OK, so this one a room in the CSE building on the third floor. So on the third floor, you exit the elevators on your left-hand side. So this is a space like a student-run co-op offering foods and snacks and beverages and coffee and all kinds of drinks. They buy things from Costco and then sell them pretty much at the price they bought. It's for grad students, or if you're undergrad but you get into research, you can also get access to the room and then get foods cheaper than the vending machine in the basement. Please let me in. It's the main reason to do research, to eat more snacks. And OK, let me open up their website. I want to show you one thing. So shape up. So on their website. OK, so they have a few things. They have this wall of shame. So see, you can have a negative balance. You just swipe your student ID and then take food from them and never pay back. That's not fine, but people do it all the time. And they have like negative $60. They all shape up $60. So if you know any of these guys, please let them know. And they also have this, what's popular this month, right? The best sold items. And number one is Coke Zero, which makes no sense to me. I like Diet Coke, but I hate Coke Zero. But anyway, so let's say if we're trying to help them to design a vending machine, right, to sell Coke Zero, just a single item. And let's say they sell it for $1.25. And you can model this as a sequential machine, taking the inputs of either $1 or a quarter coin. And whenever your balance reaches $1.25, it will automatically vend the Coke, right? A vending machine for the single item. And could you try to design this as a state graph? Right? At the starting point, essentially the balance is 0. As you put down more coins and bills, your balance increases. And when it reaches $1.25, you dispense the item. Right? And this dispense is an output action. Right? Try to design a state graph, and people can do this in many different ways. So feel free to come up with your own design and see if you want to be like a profiteer or actual student co-op leader. I mean, if someone puts down $2, what do you do? Yes. What's your choice? Yeah. Or you can eat that quarter. You can force them to buy another drink. You can return the change. It's up to you. Right. I'll give you 2 minutes to try to draw the state graph, and then get you to discuss with each other, and compare your design. Yeah, if anyone has some questions or is facing some design dilemma, let me know. And show you. Do you need any help? Yeah, you can think of you having like two input ports, right? And you don't have to like denote these inputs as some binary number. You can just say $1. You go from this state to the next state, right? Similar to that turnstile. You put down the coin, goes to the unlock mode, right? So coin is like an input that you can put next to an edge, right? Or next to a transition. What do you think? So what one? You said one's a quarter. What about 0? So you have some zeros for transition.
0 is no money.
Okay, okay. Yeah. They have a chain of quarters and until it reaches 125. It looks pretty nice. What about the dollar? I see. See. So I have some quarter chains and where's
no change given back.
No change.
I take the change.
Good idea. What about someone put down $1 and then another $1? So they go to top and then. Yep. Right, we have to make sure that this machine is fully specified. So every state has like 2 transitions based on the quarter, based on the $, right? All right, why don't we get into some group discussion? Right? Talk with people around you and then see. Well, I'm sure that you have very different designs. So talk with each other and explain how you think about this problem, how you come up with the implementation. Right, please get into groups of 2-3 people if you like. What about this part of the classroom? Can you still doing it? All right, that's all right. Or Mitchell, you can also talk with Michael. Yeah.
How would you give change?
You probably have to have another output, so you can dispense like a Coke, like return a Coke, or you can return some change. Or you could let it transition. Let's say $1 after $1, right? Transition to the 75 cents state, and waiting for another manual input, asking for refund. Right? Model the refund operation as an additional input. Eric, what do you think?
If you're here and you go past this one, but you don't land on it, so
I don't know how you deal with like chain.
kind of build up.
I see.
I guess.
I don't think this design is
Pay a dollar.
I think it looks all right. Like a chain of quarters and then a shortcut created by that dollar.
very. Yeah.
And the other thing is this machine has to be fully specified. So what if someone put down 3 quarters and then a dollar? Right? Cannot predict their behavior.
Yeah.
Oh, that's the change situation. Yeah. Yeah, that's fine. You can keep track of what is their current balance for the next code. And then you can model the change as either an actual input. Right? So they push a button for return, and then it will return the change. So actual input, actual output. Or you can choose to automatically return the change. Right? So always go back to the initial state, but in the meantime, not only dispensing the code, but also producing some other outputs for changes. Mark, what do you think? Do you need some help?
No to my idea.
Yeah. Do you know what we're doing over here? Just in general, like compare. So we talked about implementation analysis. Those are some lower level stuffs. And here we're coming back to the higher level, how to convert some behavior into a graph. And then you can, in general, model input-output behavior as some conditions associated with transitions.
Yeah.
Right? Let's say you put down a dollar, you remember that someone has put down a dollar, and you put down a quarter, and then producing a certain output.
Oh.
Go all the way back here. We would go. Or you could just.
Yeah, but then it's.
Okay. Here. We go here.
You have to have this word and then you go to the.
Right, mini or more machine, that's a choice. You can use either way. Right. On transition, that's a mini machine. Output on node is a more machine.
How do you, like, what, is there a formal way of drawing, like, an output of sense?
Well, you can just write out the return amount. Like, you don't have to model it as some binary number. Right.
That's what I have. I need to handle the refund cases. So I don't know. Well, does this work so far?
Sort of work. But what if someone put down a quarter, and then a dollar?
Yeah, that's why I have to. These are all cases.
Oh, I see.
Consider. So
Yeah. Yeah. One way is to connect them to some of the let's say, suppose they put down 75 cents and then put down a dollar. You dispense a Coke, and then they still have a remaining balance of 50. You can choose to go back to this 50-cent state. Right? And then ask for them to the manual inputs to request a refund.
So, for example, if you put $2 down, so we're So, yeah, it goes to. Okay.
All right, guys, you have another 30 seconds. Before, I'll just show you one of my ways of doing it. What is the last question you raised? Eventually, yes. You have to model the states as give them some encoding, model the input-output as some binary numbers, right? And then you can put that in a state graph, state table, and implement it. All right, guys, time's up. So as you can see, people have different implementations. Sometimes they can be very different. You have many choices, right? For example, whether to do it as a mini or more machine, right? Which means whether the output depends on input plus state or only state. You can also handle the change in different ways. You can refund automatically for the excess amount, or you can wait for another manual input to request for a refund, or you can just eat their money and then not giving them any refund. Yes. Because they're such terrible people. They know that the code costs $1.25. Why would they ever put down 2 quarters and $1? It makes no sense. They're just too stupid to deserve the refund. All right. So let's say I'll do it in I don't know, milli machine. I like milli machine better. Actually, in general, you get fewer states with a milli machine. Because you get greater expressive power of the output by being able to use some additional information from the inputs. So let's say I have a quarter, and that gives me 25 cents. I have another quarter, takes my balance to 50 cents. Another quarter, 75. Another quarter, $1. And for the next quarter, well, let's say the output will be 0, which means to not dispense the Coke. And when I receive another cent, that essentially means the balance becomes 0, but the output is 1 to give them the Coke they deserve. Right? So you see, this is actually a principle in general for designing state graph, to just figure out one of the forward path, right? The easiest forward path that gives you enough expressive power to represent all the state conditions, all the possible balances that need to be remembered. And then I'm going to create some additional transitions for the dollar bills. Every state has to have, in this case, 2 transitions, one based on the quarter, one based on the dollar. So from the start initial state, for $1, I do not give the Coke, but my balance is $1, 25 cents. I can give the Coke, right? And the remaining balance is 0. You have an exact $1.25 for the Coke. And then things are getting more complicated. If your balance is 50 cents and you put down $1, you should get a Coke, and you should have a balance of 25 cents. So I can remember that 25 cents by creating a back edge to the 25 cent state, and also giving out the Coke. $75. So with another $1, you have 175. So 50 cents in addition to the Coke. So I just have to remember that you sort of have 50 cents in my machine, and then also give out the Coke. and $1 with another dollar. That's $2, so 75 cents left after the Coke. All right, so this is this machine does not give refund, but it does keep track of your balance. At that point, if you really want to give refund, it's pretty straightforward. You can create an additional input. Let's say if someone pressed the kind of refund input, you do something. Someone pressed the refund input. Right. This is like a manual refund machine. So they can refund before reaching $1.25. And then you just handle them, each of the case separately by producing different outputs. And I mean, all of these green transitions can be connected to the initial state. Right, again, you have a choice, and there's just one way of implementing it. Refund, give out the corresponding refund as an additional output port, and then come back to the initial state. Right, finish the transaction. All right, that's it. Right, we first follow the quarter path to create all the states we need, and then try to add the additional transitions. Still remember the remaining balance after the Coke, and then finally do the refund. And this is a milling machine. And I think this is the minimum number of states you would need. With more machine, you need to have at least one state remembering $1.25. Right? With a more machine, you need a state for $1.25, and then sort of produce an output of 1 to dispense the Coke. And therefore, you see milling is more optimal than more. Right? Because the output is handled on the transition, so we don't have to exactly remember that final condition required for the output. All right, coming back to something more concrete. What we will see in this class is how to design sequence recognizers. Or pattern recognizers, sequence detectors, they really mean the same thing. A way to extract some patterns from a long binary sequence. So sequence detector is only one type of FSM that examines a string of zeros and ones, a binary string, applied at the X input. So it processes 1 bit at a time and generates an output of Z equals 1 when a prescribed input sequence occurs. So what that really means is that, let's say if I'm trying to detect whether the string contains a subsequence of 1001. I'm going to model this as an FSM and then process 1 bit at a time from the input string. And whenever I see 1001, which never occurs over here, my output will just be all zeros. And this machine runs continuously. Right? At every cycle, it produces the output, telling you whether the past 4 bit corresponds to 1001. If not, produce a 0. If yes, produce a 1. So here's a concrete example for the pattern 101. So let's say you send me that input sequence X, a very long binary string, and I'm trying to find if there's a subsequence of 101. Right? Once you reach the 6th bit, I have just observed 101 from the past 3 cycles, so output becomes a 1. And then you have another subsequence of 101, produce an output of 1. And finally, over here, you have 101, produce an output of 1. This machine includes overlapping patterns. So you can see there's 101, and reusing the 1 as the beginning bit of the next sequence as a valid way of starting the next sequence. So this is called an overlapping detector. You see, this is a FSM with 1 bit input, 1 bit output. Process 1 bit at a cycle, producing 1 bit output each cycle. Right. So let's say how we do it. Well, we sort of do it in a similar way as that vending machine. We first try to handle the correct pattern to build the states, the things that worth remembering, and then fill out the remaining transitions. So starting with a null state, and let's say now I'm building it as a more machine, which means output depends on the state. So at the beginning, output should be a 0, indicating that I have not seen the pattern. And if in the next 3 cycles, I get a pattern of 1, 0, and 1, my output should be 1, right? Telling me that I've just seen that pattern in the past 3 cycles. And this is the correct path. Let me use a different color so that it's a little bit brighter. Right? At each state, I'm essentially remembering some information about my most recent pattern history. The first state is sort of like remembering that I've just seen a 1. Second state, I've just seen a 1, 0. Third state means I've just seen 1, 0, 1, which should produce an output of 1. And for all the other states, output should be a 0. And this allows me to detect 1, 0, 1. Cycle 1, you send me a 1. Cycle 2, you send in a 0. Cycle 3, sending a 1. Output becomes a 1. All right, similar to that quarter chain we constructed for the vending machine. And now it's time to fill out the remaining transitions. Every state, again, has to have 2 transitions, one coming out of the 0 input, and the other coming out of the 1 input. So at the beginning, if I see a 0, well, 0 is not part of my sequence, and I don't even have to remember it. I can just stay at the initial state. Right? Nothing significant for me to remember. So now moving on to the second state. We have already seen a 1. If we see another 1, right, essentially my most input pattern is 1, 1. What's going to happen is that, well, the most recent 1 could be the first bit of the sequence. So I only have to remember the most recent 1, which means I can stay at the current state. Right? So the third state, I've already seen a 1, 0. Well, I'm very close to the pattern I need to detect. But if I see a 0, right, suddenly the hope is all gone. It's not my sequence. And 0 is not even the beginning of the next sequence. So I come back to the initial state. And finally, 1, 0, 1 is the place where I claim success. I have already seen 1, 0, 1. If I see another 0, right, 1, 0, 1, if I see another 0, well, this 1, 0 could be the first 2 bits of the next sequence. Right? I'm essentially reusing the 1 from the current sequence as also the first bit for the next sequence. So if I see another 0 from the 1, 0, 1 state, I need to remember that I've seen a 1, 0 within the 2 most recent bits. So I'll come back to the 1, 0 state on the input of 0. And finally, if I see a 1, so 1, 0, 1 followed by another 1, well, this could only be the first bit of the next sequence. So I come back to the 1 state. Right. The general procedure of designing sequence detectors on the bottom right. In general, we first handle the correct sequence to construct our states. These are the information worth remembering. And then we add transitions for the remaining transitions. Yeah, any questions? Right, here's just a better picture. Essentially same as what I drew earlier. All right. Now again, I have another exercise for you. Could you try to design this sequence detector in a milling machine for the very same sequence of 1, 0, 1? For a milling machine, I specify the output on transitions instead of states, because the output depends on the input value. Right, again, to design the sequence detector, we follow more or less the same procedure. Number 1 is to handle the correct sequence. Oh, I can write better. Number 2 is to fill out the remaining transitions. Right, fill out the rest. So I'll give you a minute to construct the FSM. Right, do as much as you can. Right. In the meantime, I'm gonna draw some, like a partial FSM on the screen, if you need a bit of extra help. So I'm trying to handle the correct sequence. 7. So what do you think from the 1, 0 state? If I see a 1, where do I go?
1 next.
Add another state? You don't have to. In that previous Moore machine, we have 4 states. But mini machine, again, gives me a bit of saving. The 3 states are all I need. Not necessarily, because you see, if you have 1, 0, 1, the 1 could also be the first bit for the next occurrence of the sequence. Yeah, we go to the 1 state. Yeah, just remember the right amount of information by your state machine. Right, 1, 0, 1, I already produced an output of 1. So the only thing worth remembering is the most recent one, which could be used by the next sequence. All right. So time is up. So again, let's first try to construct a machine for the correct sequence. We have 1, we have 0, and if we see another 1, we should output a 1. Right, on the next transition, regardless of where it goes, if I have an input of 1, my output should be a 1. But where does it go? Well, again, think of 1, 0, 1. You do produce an output of 1, but the 1 can also be used as a first bit for the next occurrence of the sequence. So we actually go back to the 1 state. The state specifying a most recent 1. So think about if you run it as 1, 0, 1, 0, 1, 0, 1. Suppose this is your input pattern. You go 1, 0, 1, produce an output of 1. 0, 1, output of 1. 0, 1, output of 1. So it does work properly for that overlapping 1, 0, 1 sequence. Right? So now let's move on to the remaining transitions. At the beginning, if I see a 0, that's not part of my sequence. State number 1, if I see another 1, again, it will produce a self loop. Output of 0. The 1, 0 state, if you see a 0, well, the 1, 0 becomes meaningless. So you come back to the initial state, produce an output of 0. Right, now the FSM is again fully specified. Every state has 2 transitions. And they all go to one of the valid states as the destination. Right, if you compare the two, Moore machine takes 4 states. Mini machine takes only 3 states. It's more optimal. But you get this optimality at a bit of cost in terms of the reliability of the output. You see over here, think of this as an actual circuit, and when you change the input, the output will change immediately from the combination logic. So depending on when you change the input, the output may get ready a little bit earlier than you expected or a little bit late. But for a Moore machine, the output will only be updated at the positive edge of the clock when the state changes. So you get a more deterministic output behavior from the Moore machine. Right? We never get anything for free in this game of designing digital systems. And in general, you can specify 3 types of sequence detectors. What we have just seen is an overlapping specification. We allow patterns to overlap, and we still produce ones for these overlapped occurrences of the same pattern. You can also design a pattern recognizer for non-overlapping pattern recognition. So in that case, whenever you complete a pattern, essentially reset. And then this overlapped pattern is not recognized. Right? So I do not produce a 1 over here because I only detect non-overlapping patterns. There's a different way of specifying pattern detector, which is called disjoint window recognizer. Disjoint window. That means I create a fixed width window, and the pattern must occur within that 4-bit window. Right? In this input pattern, let's say 0110 in a 4-bit disjoint detection mode, that pattern has to appear exactly within the first 4-bit or the second 4-bit or the third 4-bit. When it crosses the 2 windows, it's not identified as a valid pattern. And therefore, the output will be 1 only if the pattern fits exactly within a 4-bit window. And this kind of pattern recognizer is useful if you are dealing with, let's say, a sequence of BCD representations, binary coded decimal. Every decimal digit is represented by 4 bits. Let's say if you're trying to figure out if you have digit number 6 right, within a long sequence of numbers. And over there, you have to recognize every 4 bits. Every 4 bit carries a specific meaning. And as it turns out, you can design a state machine or state diagram for each type of these recognizers. So here's a different example for 0110 recognizer in overlapping and non-overlapping mode. They work pretty much the same for the forward pass. When you detect the 0110, so far, they work identically. The only difference is how we handle the kind of overlapping scenario. After the detection, for the overlapping recognizer, I'm going to remember the most recent 0, because that could be the first bit of the next pattern. For a non-overlapping recognizer, the edge comes back to the initial state, which means I've completed that detection, and the next pattern has to start fresh. And this is a new way of denoting multiple conditions and output values for a transition. You just put a comma in between. So this says on the input of 1, I produce an output of 0, goes to this state. On the input of 0, output is a 1, and again, I go to the same state. The only difference between these two machines is when you complete the detection, where do you go? Right, versus this one. And disjoint window detector is a little bit more complicated. It's not that complicated. Again, the principle is to first design the correct path. 0, 1, 1, 0. I come back to the initial state because I operate within the 4-bit window. So after every 4 cycles, I should come back to the initial state. Right? There, with the window detector, overlapping will never happen, or it's not recognized. That's how we create these bottom states for the correct sequence. And we also need to make sure that even if a bit goes wrong, we still want it to spend 4 cycles within the current window before moving on to the next detection window. So we create a lot of rejection states, like creating them as a parallel path compared to the correct states. Whenever you see something that does not match your pattern, we go to the top. If the first bit is a 1 within the current window, we know that it's not our pattern. So we go to the rejection path. But we have to spend 4 cycles in that rejection path before opening up the new window for the next 4-bit pattern detection. So whenever we see something wrong, we move up to the top path. So this one means reject 1 bit, reject 2 bits, reject 3 bits. And then finally, I'm going to reject 4 bits, which means within this 4-bit, I do not have the pattern. And now I can start the next detection window. So 0110 is the only way to traverse through the bottom path and producing an output of 1. All the other patterns will go to the top, spend the 4 cycles, like get stuck for 4 cycles over there, before resetting. Yeah. Anyone has some questions about this? All right. So with these 3 major types of detectors out of our way, you can also specify some variants. Sometimes you care about multiple patterns, and you want to detect them simultaneously. So let's say we want to detect pattern 011 or 1110. If either of these 2 patterns occur, I want my output to be a 1. Right? We used to detect just a single pattern. You can also build an FSM to detect 2 patterns. So how do we do it? The principle is sort of the same. We first create the correct path for these 2 patterns, and then try to fill out the remaining transitions. So I have an initial state, which means nothing. I guess I will use a milli machine. Right? This machine is pretty big, so if I use more, it's going to have maybe 1 or 2 additional states. So for simplicity, I will do a milli machine. On one side, if you see 0, 1, and 1, well, it's a milli machine, so I don't know where that final transition goes. Right, so if I see a 1, I want my output to be a 1. Output is 0 on the other transitions. So I've seen a 0, I've seen a 0, 1. I'm going to create a different path for the bottom, the other pattern. So 1, 0, sorry, 1, 1. 1, 1, 1, and see another 0. I want my output to be a 1. That is the correct sequence. Right? The final transition, these final transitions don't necessarily go to new states. They could probably cycle back, as what we did for that earlier mini machine example. But that is the output value. Right? Output value on the other transitions will all be zeros. And what I put over here, this is not state encoding. This is only the meaning of the state. Over here, I've seen a 1 in my most recent cycle. I've seen 2 1s in the most recent 2 cycles, etc. Right, so that is not encoding. This is not encoding, but the kind of pattern meaning. And then the next question is to figure out the remaining transitions. Where do I go? Right, for example, 0, 1, 1. 0, 1, 1, which is the correct pattern. Where should that transition land? Want to figure out? Yeah, Rona? No, go ahead.
I was going to say to the single one.
To the single one? Why is that? So you're proposing we go here? You're saying the 1 could be the beginning of the next pattern for that 1, 1, 1, 0? Yeah, Cleland? Yeah, Cleland is saying that we can also go to 1, 1 state. Right? The 2 most recent ones can all be used for the next, the second pattern for the next occurrence. So in fact, we want to remember as much information as possible to allow maximum overlapping of these 2 patterns. So we can go to 1, 1 state. That is the meaningful information for the second pattern. Right, so I'm going to modify it a little bit. On the 1 input, I produce an output of 1 coming to the bottom. Right, what about the 1, 1, 1? And you see a 0. 1, 1, 1, we see a 0. Well, 0 is the only meaningful bit for the first pattern. So we come back to the top. And then produce an output of 1. All right, there's still a few missing transitions. So 0, I see a 0, nothing happening. 0, 1, I see a 0. Come back to the initial. At the bottom, 1 sees a 0, so goes to the top. 1, 1 sees a 0. Well, there's so many transitions going to that 0 state. And 1, 1, 1 sees a 0, that's a correct pattern. If you see another 1, well, we stay at the same state. We have 3 1s in the most recent 3 cycles. So, but the output is still a 0. Right. So by breaking up this task into 2 different steps, number 1, construct the correct machine. Number 2, fill out the remaining transitions and find out the correct destination for the detecting condition. You get to complete the FSM. This is a complete FSM. Every state has 2 outgoing transitions on the 0 and 1 input. So no matter what kind of input sequence you supply to it, it will produce the right output. Right. There's a different kind of sequence detector, which is a more constrained, but I would say you don't have to worry about it, so don't worry. Right, you can let one sequence detector to be the precondition for starting the execution of another, and this is what we're showing over here. Top and bottom, we have a parity counter. Right, so I have a parity counter. And when you go from left to right, that means you're trying to recognize a pattern. And this one will only produce an output when both of those patterns are satisfied. The previous one is either this or that. You can also design a kind of joint sequence detector when both conditions need to be satisfied. Right, but don't worry. So that's everything for today. We revisited the sequential evaluation process through that large state table, going from the inputs to the combinational function and then through the characteristic equation. We also went backwards, starting from the behavior, then using the excitation table to build the truth table and also the K-map for the combinational logic. And then we talked about how to design state graphs from the behavior description for that vending machine as a motivational example, and more concretely for the sequence detectors. 3 types. You should know how to design each of these 3 types. And that's everything for today. And the workbook is due on Tuesday. Monday is a holiday, no lecture, nothing. So just submit the workbook by Tuesday. Yeah. This one? Yeah. Yeah.
I have a question about construction.
Yeah.
So this means that the Q1 will come here.
Yes.
Oh,
Yes.
and
And Q0 will also come here.
oh, right.
Yeah.
So the current state means when
Yes.